Um, I don't need the light now, but we'll need it in 10 minutes or 5 minutes even. Yeah. I'll switch it off, I think. This has been really a fun week, I must say. And now I'm also amazed by all the projects you suggested. So great work. This is fantastic. And I hope I can get a little attention from you for my final lecture. It's going to be about non-equilibrium mixtures and foams, because if you look here into thermodynamics, you have lots of patterns also in thermodynamic systems. One object we didn't really talk about yet is the lipid bilayer of a living cell that spontaneously forms by self-organization, because the lipids that make up a biological cell are hydrophilic and hydrophobe, so they have polar ends, and they just like to hide away from the water, and by that they form these beautiful bilayers, which are really key for any kind of biological cell. The second picture you see here is a simulation from Andrei Koshmil's group. Andrei was working a lot on multi-component mixtures and had some beautiful theory about that, and this just shows you if you have many components together, you can form phase separation and bubbles and whatnot, which are quite beautiful, and their coarsening laws, very similar to the coarsening laws that you might remember from the talk of Nigel on two-component mixtures. And last but not least, there are foams, and these foams exist in many different forms. There's a lot of things I could tell you about this. These are pictures from Doug Durian's lab, who has done beautiful experiments on these foams, where you see this is like a cellular structure with all kinds of different sizes of these foam-like cells. You have foam bubbles with 5 corners, with 6 corners, with 7 corners, and it's just very intriguing to study the coarsening behavior of these foams and compare the coarsening behavior of the foams with the coarsening behavior that you see with mixtures. And all of this is basically dominated by a single single physical effect, which is surface tension. Right? This is the main driving force between underlying all these phenomena. And so let me illustrate to you what surface tension is. If you talk about a thermodynamic system, it's a very basic concept, and what it means is if you have a surface, say between the liquid and the vapor above, then the particles in the bulk of the liquid, they have lots of neighbors surrounding them, and the particles on the surface are a bit lonely. They're missing some of their friends, some of their neighbors, and because of that, you have a different type of energy at the surface. And that's what makes up the surface tension. And you might also notice it matters here whether you are on a bulge or on a valley, because that changes the number of neighbors. And since you change the number of neighbors, you change the surface energy, and therefore you change the corresponding tension that you experience. And there's a famous law that was derived many, many years ago by Gibbs-Thomson. And this famous relation, Gibbs-Thomson relation, relates a few important quantities that appear in the thermodynamics of mixtures and of foams in a similar way. So what you have is a jump of density. So here's a high density in the liquid, there's a low density there, and this delta rho is the difference between the densities. And on top of a jump in the density, there is a chemical potential shift, delta mu, and this chemical potential shift, delta mu, is facilitated by the right-hand side, which contains a surface tension, That's the interface energy per unit area that I was talking about, and the curvature of the interface. Okay? So it tells you that there are shifts in the chemical potential if you curve the interface, and those shifts in the chemical potential, they depend on the curvature that you have, right? They depend even on the sign of the curvature that you have. So and keep this in mind, this important relation. So shift in chemical potential is induced by curvature, and the proportionality constant is the surface tension. Now this relation is behind a more macroscopic picture of phase separation in binary mixtures. So if you were not to use scaling laws, but if you were to really study how the coarsening happens in a binary mixture, you would need to use that Gibbs-Thompson relation and derive the corresponding fluxes and currents in the system, and thereby determine the Ostwald ripening process and all the prefactors and all the details. Now, let me switch here to foams. And I'll give you an introduction into foams. It's kind of foam 101. And I confine myself to the simplest case of foams, which are two-dimensional foams and which are dry foams. There's much more to say, and there's a nice book on the physics of foams. I think, I don't know whether I pronounced the name correctly. It's Weary and, yeah, Weir, that's the name, okay. So let me talk about two-dimensional foams. And I'm doing all that and show you the Gibbs-Thompson relation and show you the basics of foams, because later on I'm going to tell you that even outside, or in particular outside of thermodynamic equilibrium, you have similar phenomena, macroscopic phenomena, that give rise to an effective surface tension and effective laws that are similar as you find them in these thermodynamic foams. And you have to kind of appreciate the difference to what we have there. So what I want to do here now is to say, let's first look at 2D foams and also multi-component mixtures from the perspective of thermodynamics. So first, let's look at a three-component mixture. You heard about two-component mixtures. Now let's take three, and let's call the components A, B, and C, and the corresponding phases that are A, B, or C rich, the phase A, B, and C. And then in distinction to what we had for two-component systems, you can now have an interface between a phase, a B phase, and a C phase. And at the vertex, you will have surface tension meeting each other, surface tension vectors meeting each other. So let me draw the corresponding vectors for the surface tension. So in general, those lines are not straight, they may be curved. I drew them straight. So along the tangents of the films meeting this vertex here, you have surface tension sigma between the AB phase, sigma between the BC phase, and sigma between the A and the C phase, and all three of them are vectors. The first law that you have for foams is a very simple one. It says that there must be force balance at such a vertex in equilibrium, and that, that law is called the Neumann law. And it simply states that if you add up all the three surface tensions, so sigma AB, sigma BC, plus sigma AC, that equals to 0. Okay? This is a wonderful law, and if you want to derive that from thermodynamic considerations and not from such a force balance as I write it, it's actually not that easy to show this Neumann law. And if you like, I can point you to some literature where you can find a derivation of that. Now, a speciality of mixtures, and in particular foams, is, which are also characterized by interfaces. They're not interfaces between different phases. They just define the bubbles that you saw in the corresponding picture just a minute ago. One of the basic laws is the fact that these angles form 120 degrees. That's one of the famous Plateau laws that you can define. All right, so that's one important feature of two-dimensional foams, known the Neumann law. And I like these kind of laws because they make no reference directly to any microscopics. There's no particles anymore. There's no microscopic picture. It's really just the macroscopic behavior of the system that comes about because you have this macroscopic object or mesoscopic object of a surface tension. Now let's talk about another feature of these foams, which you might have anticipated from looking at the pictures from Doug Durian's lab. They're statistics of foams. They have different numbers, they have different sizes, the bubbles that you see, and you would like to make a statement on that. Well, this is something which relates the physics of these objects to a very powerful tool in mathematics, namely topology. There is a quantity called the Euler characteristic, that's called chi, and this Euler characteristic is a topological invariant. It just depends on very general properties of the space that you're in. And it says that if you look at a foam, a polyhedral structure, this polyhedral structure has faces, it has edges, and it has vertices. Right, so if I were to draw that, I have here a face given by a hexagon, and this face here has 6 edges, and this object here is a vertex. So you have a vertex, you have an edge or corner, and this here is a face. Okay, so that's an invariant, and you can now use that invariant to make some very general statements about the foams. So first thing you should notice is that if you look at the edges, 3 edges, they must meet at a vertex, a very obvious fact, as you can read off from the picture here on the right. And the second fact is, and an edge that you see there, so let's say this edge here, right, it's connecting 2 vertices. So an edge links 2 vertices. And that has an implication. So if you put what I put here in words into a mathematical relation, it says 3 times the number of vertices has to be the same as 2 times the number of edges that you have in such a polyhedral foam-like structure. And, right, and an edge separates 2 faces. Right? Also quite obvious, right? This edge here separates this face from that face. And that means if I again make the counting, then twice the number of edges that you have in your system is equal to a sum over all bubbles with different numbers of edges. So 6, 5, 4, 1, 2, not 1, but 6, 5, 7, for example. And you count the number of edges, n, and you multiply this with the frequency that they occur in your system. That's the third equality that you have. Okay? So just by the very structure of a polyhedral, these are strict relations. Okay, Fn, if you missed it, is the frequency of edges of a given face. So now let's use that and rewrite this topological invariant, the Euler characteristic, in terms of the equations that we have. So we have f minus e plus 2v. We can replace the v by 2/3 of e and then subtract minus e. So I do get from that this is f minus 1/3 times e. Now let's rearrange that. As I rearrange that, I have the number of edges is the number of faces minus the topological invariant. Let me divide this by f, right, and take the limit of a large system size where you have many, many, many faces and basically an infinite number of faces. So as f goes to infinity, this is 3. Yeah? The ratio of edges to faces is 3. Now let's take the last relation that we have here and take the average over all that you have. So this here on the right-hand side is almost the average. If you multiply and divide by f, you get the average of n times f. So with the third relation, we then get 3 times e is the average number of edges that you have in a bubble times the number of faces. And now I combine these two relations, and here we go. You get the typical, the mean number that you should have in these systems is 6. It's a very strong statement, right? So typically, for large enough foam, we look at it, it should have mostly cells with 6 edges. Now let me continue and ask about not the final state of this, but ask about the dynamics of such a foam. How would it evolve in time? And as said, I'll focus on 2D dry foams for my analysis. And the only thing I want to use, surface tension. Oh yeah, sorry, that's correct, thank you. Yeah. Otherwise I won't get what I say I get, right, thanks. Okay, so importantly now, the only thing I would like to use for the following analysis is the fact that you do have surface tension in this system. And I arrive there by looking first at what's happening to a foam when you think about a foam as a dry foam with some air in the bubbles, and the air in the bubbles creating pressures, and the pressures can be different from bubble to bubble. Okay, so let's take that. Let's look at a particular bubble. Okay, so let's say we do have now two bubbles that face each other. The area of the bubble on the left I call A1, and the pressure of the bubble on the left I call P1, and this similar for the area and pressure of the bubble on the right-hand side. I drew the film connecting the two bubbles as straight. That's only straight if the pressures are the same on both sides. And if they're not the same, it will bulge out. So here it will bulge out to the right if the pressure in the left bubble is larger than the pressure in the right bubble, and I would have the reverse if the pressure on the right would be larger, and vice versa. Yeah, please. The areas of the bubbles.
Okay. Oh.
So if you take this object here,
So
that's just the area of that. Yeah. Now, in addition, I want this here denoted the length of the film between the bubble 1 and 2, and call this length 2. So it's the neighbor 2 of bubble I. In general, I will call Lj the length of the neighbor j of bubble I. Now let me write down an equation that has a certain set of assumptions in it, but they are pretty straightforward. So as you have such a film between two bubbles, the area of the bubbles will change. Why would it change? These films are not tight. There's flow of air between the films. Okay? If you have flow of air between the films, what is driving that flow? Pressure, right? So a reasonable assumption is to say that the pressure difference will give rise to flow between the different bubbles, and that then results in the area change. Okay? And will be such that area is reduced with a certain coefficient that I don't know. It's a material parameter of the foam that I'm looking at. There's a pressure difference between my bubble I and its neighbor j, and I have to sum over all j, which are nearest neighbors of I. And I'm missing something here, of course. The flow will be proportional not just to the pressure difference, it will also be proportional to the length of the interface between the two faces, right? So this will be Lj. All right. So what do we know about the pressure difference? If you have a bubble, a sphere, and there's pressure in it, there will be pressure in it, and there will be a pressure jump. That's called the Laplace pressure, right? This Laplace pressure depends on the radius of the sphere that you have, and here, in general, it will depend on the curvature that you have. Okay, so we have Laplace pressure, which means that my pressure jump between the two cells I and j will be the curvature that we have of my cell j, and the object the response coefficient that we have here is sigma. And remember, sigma is the surface tension. And that's the curvature, to be precise. It's the mean curvature, but we don't have to worry about this. It's a two-dimensional system, so curvature is fine. All right, what does that mean? Well, I'm rewriting now this law here. So as I write this, this is minus this phenomenological coefficient that we have. And then I have surface tension as a material parameter, and I need to sum over all the different neighbors, and this will then be proportional to Lj times the curvature kappa j. Good. Now let's write this in a way that uses, the feature of such a bubble. So this will be curved because the pressure will bend these different film boundaries. Those are here are vertices that connect this bubble to the neighboring cells. Right, and I call this curve that you see here gamma j. And I can rewrite then the length of the interface that you have here as a line integral over this curve, which then gives you the length. So dt AI is the same as minus the permeability coefficient alpha, the surface tension sigma, the sum over all j, the line integrals over these curves, ds, and then the curvature kappa j. Okay? But now you're in business, because there's this final object that you see here. This one here. This one here, one knows how to write in a different way, namely in terms of macroscopic, so to say, properties of the cell. The relation we use now is one of the very famous relations that Gauss derived for differential geometry. Okay, so there's a key point here. So in the next step, I use Gauss-Bonnet. And as you do so, you get the following equation. I have to add something here. So if you go along the periphery of this bubble, you can define angles theta j. These are the kinks that you have as you go from one film to the next. And the Gauss-Bonnet theorem tells you that the relation I wrote is, so this is the prefactor, and Gauss-Bonnet says this integral on the right-hand side is 2 pi minus the integral now over the area of bubble I times the curvature. Sorry, I should write here. There's different times. This might be a problem here. So let me call this kg minus sum over j theta j. Okay, and this kg is, yeah, please.
So when we say theta j, is that the average theta j across all the kinks in the cell, or in
the theta j is the angle that you have at the following the line j. So a particular value, but they're all the same, as I say in a second, because I have Plato's law.
So here the indices are the indices for the vertexes. It's not for the.
The index for the edge and the vertex is basically the same, right?
Yeah.
Yeah. And what I should say before these theta j's here, this here, is because of Plato's law, 120 degrees. So this here is pi over 3. Yeah.
Isn't the curvature that appears in Laplace's law and the curvature that appears in the Gauss-Bonnet theorem different curvatures?
Yeah,
one is intrinsic and the other is extrinsic.
It's different. It's definitely different. And that's a very, very important point. The curvature that you have in the derivation that I made at first is the mean curvature. The curvature that you have in Gauss-Bonnet's theorem is the Gaussian curvature. That's why I indicated it with kg, and the Gauss curvature for a flat interface is 0.
Okay.
Right? That's the important point to realize here. It connects the curvatures around the boundary with the Gaussian curvature of the surface that's connecting the edges. And since we have a flat, dry foam, the Gauss curvature is 0 of the surface, right? Yeah, you had a question in the back? Yeah.
So I wanted to ask if Newman's law is also true when there's dynamics.
Neumann's law is also true?
When there's dynamics in the system, so when you're not in equilibrium and there's changes in area.
Well, the sum is 0 in mechanical equilibrium. If you're out of mechanical equilibrium, it's no longer true. There's a driving force coming from the difference between this and 0. That's what makes the foam move. Yeah, because that's a static law in equilibrium. Yeah.
Sorry, but you still have this 120 degrees, or that's only in equilibrium? That's what's confusing me.
That's roughly true all the way.
Okay, thank you.
Yeah. Other questions? Veronica?
I think it was related to that comment. So when you talk about Euler's relationship, so that's for any like tessellation in 2D or 3D, right?
Yeah. 2D for now.
Yeah, so you could change the
Yeah, because 3D is a bit tricky. But let me...
Yeah. But then you show the foams, and then you say, okay, this is, you're going to get 120 because the tensions are the same.
Yeah.
But topologically, it's not really the case that 3 edges must meet at a vertex. Like you could have topologically 4 meeting or something like this.
Yeah, you could have 4. And
so when you write that down, you're already assuming that
Yeah.
you're thinking about a surface tension minimizing system.
Yeah.
Which equal, yeah.
Yeah.
So it's
Yeah.
not like a mathematical proof of.
No, it's not a mathematical proof.
Yeah.
In this, I'm using mathematics to prove it, but I'm using the fact that this is surface tension driven,
Exactly.
and therefore it's arriving at a minimal, minimal surfaces. That's what I'm using, heavily, right, heavily. And it's key to understand that once you know this is surface tension and that's driving the physics, the rest is math. Other questions? We're almost there, right? This thing here is 0 because you have a flat surface there. Well, and then if you write this out, this is pi over 3, alpha of diffusion, so the permeability, sigma Ni minus 6. And this law here, it's another important law that we have. That is called the von Neumann law. right? And it says, right, independent of whatever detail, right, only using the fact that you have surface tension, 6, also bubbles with 6 edges will stay constant. Those with 5 will what? Shrink, okay? The 7s grow. And you can continue this with other number of edges. It's quite strong a statement, okay? And let me reiterate, it doesn't use much, the existence of surface tension. That's it, and math. If you continue this, dot, 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 and I leave this out, you can also ask yourself, what is the coarsening law for the area, or let's say the length, the size, the typical distance. So if this is the area, then L is the typical size that's defined by that foam, will also change over time. We heard for a 2-component mixture is T to the 1/3. Here, the coarsening law is T to the 1/2. And the way you can get this is, again, you make an assumption that there's universality in the bubble size distribution, or you actually work it out step by the mechanics. Concerning the scaling law, there's a very nice and beautiful story behind that. So in 1990, Joel Staffens, when he was postdoc, he looked at foams, and he made copies of those foams just by going to a Xeroxing machine, copy machine, and copied his foams, and then he measured the different sizes of these foams, and from these pictures then identified the scaling laws. I can give you the paper. It's a beautiful paper. It's something he did when he just started his postdoc and didn't know what to do, I guess. He did know, just kidding, okay? So this is kind of the 101 for dry foams, and you'll see we have laws. We have a Neumann law, which you can either read as something coming from a mechanical equilibrium, or also a consequence of thermodynamic equilibrium. So this is a free energy minimum that you have here that gives rise to this. So this is essentially, it's an essential way linked to thermodynamics. If thermodynamics breaks down, you're not supposed to actually get this law as guaranteed. Doesn't have to be. Right, then I said there is surface tension, and once you have surface tension and get these minimal surfaces, then there is von Neumann's law giving you a very strong constraint on the dynamics of the areas. All right, now let me go back to my slides. So this is just showing you some pictures, and this here is actually a simulation which runs incredibly slow. So if I speed it up, you'll see the dynamics of such a foam, where you see these 5s, right? The 5 here in the middle is shrinking, and bang, it's gone. And here, at this particular point, there's a transition where you actually do have more than just 3 of the edges meet, right? This is called a transition, topological transition in the foam structure, and then it goes on. So this is the von Neumann law based on geometry. As the structure of the foam changes, there are certain transitions that are characterized that change the topology, and the one that you just saw is a T1 transition where you go from 2 vertices with 3 edges meeting and now having 4 edges, and this continues then building a new boundary, and it gets 3 edges again. And you can also have a T2 transition where a triangle shrinks to 0. All right? This is something we just learned. This is something I showed you. The average number is 6, and this now comes to the questions that I would like to ask. and like to study with you in the remainder of my talk. So questions you can ask now is there an analog of surface tension in a non-equilibrium system, and what would it be? Okay. Can have non-equilibrium systems form supramolecular structures, so like the micelle, these mixtures or foams or bilayers even. So is that possible? And how would you classify these non-equilibrium systems and the transitions between them? And could you formulate laws? Similar laws as you see here. Could you formulate a Neumann law, a von Neumann law? Would they change? Would they be the same? So what are the mesoscopic laws that one can define or find for non-equilibrium systems? All right, so that's my question. And now let's go back to facts, to something you see actually in biological systems. Here, what I show you, now I can switch off the light. So here you see a very famous biological model system, which is the C. elegans zygote, and that has been studied by many people. And one particular paper I would like to highlight here is the paper from Stefan Grill's group at Dresden. And they have studied the C. elegans zygote and the pattern formation that you see here in quite some detail. That's a time sequence out of a movie. And what you see is that there's two different proteins labeled in blue and red. And over time, it nicely defines the left half and the right half of the cell. So this protein patterning system based on the PAR proteins is important for defining cell polarity. The model behind this, that's really a model. This is a very simplistic type of description of what's going on. Behind that, as usual, is a huge network, but this here gives you the main picture. So the main picture is that there are two proteins called A pars and P pars. So for anterior and posterior PAR proteins, they attach to the membrane, and when they attach to the membrane, they fight. They fight such that they kick each other off from the membrane, and then it makes sense, right, intuitively, that they would like to be in separate places and keep the fighting just to a small interface between them. Right? It minimizes the kind of fights that you have. Now, as you observe that, you ask yourself, how is this interface here between those domains? How would you describe that? Not at a microscopic level, right? Because you could now have lots of models that describe that, calculate them, do a diffusion reaction dynamics, and study what happens. You would like to know, if I hold myself blind to any kind of reaction kinetics and just observe the interface, how would I describe the interface of what happens? Now, so making a more detailed model we did anyway. So Rafaela, in her PhD thesis, made a model for this A-par, P-par system. And here are her simulations. And the simulations she has performed is here for an ellipsoid and for a prolate shape, right? For a cigar and a prolate-shaped cell. And what you should note, what you should look at now is how is the interface forming and what's happening with the interface. Okay. Okay, so that's happening in both cases. So what do you notice? So ask yourself, by symmetry, what will be possible? Go ahead, just don't be shy.
In principle, this midline could be along any of the symmetry axes of the...
Yeah, it could also be around here, right? Or it could be around here, the interface. It doesn't have to be in the way I drew it. Symmetry would not dictate that, right? But what's different between an interface here along this line and an interface along an equator there? The length, right? Which one is shorter? The one you get. Okay, the same is true here on the right-hand side. So we were puzzled because that means this interface, which is created by the diffusion reaction system, has the same macroscopic feature as an interface in a foam or in a thermodynamic mixture. It minimizes the length. Okay? Well, and then you wonder, is there something I could define and calculate that is a surface tension, and what would drive that surface tension? Right, surface tension in thermodynamics, just to remind you, hopla, I didn't change that. So surface tension in thermodynamic equilibrium for a mixture or a binary, tertiary, whatever mixture, comes from interactions and different levels of interaction depending on the curvature. So it's ultimately encoded here in the Gibbs-Thompson relation. A system that's based on chemical reactions has basically no interactions. It has interaction in the sense that chemical reactions appear, so you form dimers, you kick each other off, you attach and detach, but there is no pairwise attractive or pairwise repulsive interaction as you have it here. Okay? So here the pairwise attraction is the reason why you have surface tension. And there cannot be the reason for this, whatever we find as surface tension in the corresponding pattern forming system. So we have to find something else that's the reason for the surface tension that you have. All right, now, the way you can approach this is by beautiful math. And Henrik Weyer and Tobias Roth, those are two PhD students in the group, they really worked through all the analysis in the proper mathematical detail. And what I'm going to tell you now is a story that's more phenomenological, where I try to help you in your intuition about what's driving surface tension here. Because the math is quite involved. Lots of asymptotic expansions, etc. So I showed you this picture, right? And I talked about key design principles of that system. And one key design principle was that there's cycling between the membrane and the cytosol. There's a flux that goes around in cycles like so. These fluxes do not exist in thermodynamic equilibrium. They're excluded in thermodynamic equilibrium because you do have detailed balance and you have pairwise fluxes that cancel each other. So any cyclic flux, according to Kolmogorov's theorem, has to be an indicator for non-equilibrium states. Okay, so that non-equilibrium state here has a cyclic flux. And that's the only thing I'm going to use. I'm only using that there exists a cyclic flux, and that has a priori nothing to do with this particular mass-conserving diffusion reaction system, because diffusive fluxes, because cyclic fluxes are generic in non-equilibrium systems. They're always there. They have to be there, otherwise they would not be in non-equilibrium. And now let me use this only fact, cyclic fluxes between the membrane and the cytosol. Good. Now, and please ask questions if you can't follow, because that's really the key argument that will come now. The rest is, so to say, consequences of that. So let us focus on our C. elegans zygote, and let's imagine we have a boundary between some high density phase and a low density phase on the membrane. And let's cut through the boundary like so, and look at this boundary along this cut on the ellipsoidal interface, ellipsoidal boundary of the zygote. Then there will be a concentration of these proteins on the membrane, so going from high density here to the interface to a low density on the other side, here on the light blue side. There's going to be a corresponding interface in the cytosol, which is just the other way around and a bit more shallow because diffusion in the cytosol is faster than diffusion in the membrane, and that's why you have this sharp boundary that you have there on the membrane. Now we have cyclic fluxes, right? These cyclic fluxes are the reason you maintain the interface, and that's what I'm putting in here. That's an assumption. So I'm saying the interface is maintained by fluxes that are cyclic. Diffusion would kill my interface because there's flux of particles along gradients in this direction. Here I have an attachment zone where the particles that are flowing this way are traveling towards the cytosol. They're traveling back, again because of diffusive fluxes, to this side, and they're taken up by attachment from the cytosol to the membrane, and thereby you have the cyclic current that's at the interface and defines the interface. So far, so good? All right. Now, let's look at this. It's a bit complicated, but I'll help you through. We are now looking on the surface, right? So we're not cutting the surface, we are looking on, this is the top layer of that surface, and this here is the interface on the membrane between the high density phase and the low density phase, okay? So I'm looking down on this. Now, here I'm looking at an interface which is bending up, and here it's bending down. So you have positive curvature, depending, of course, on the signs you choose. So here's one sign of curvature, and here's the other sign of curvature. Let me call this positive and negative curvature. You will have an interface, right? This interface here is here. This is the attachment zone here. This is the detachment zone now looked from the top. And now there's a very simple geometric fact that you know if you take your notebooks and you fold it, you will stretch the upper part and you will compress the lower part. So geometrically, this orange area is larger than the corresponding dark bluish area. But here's the key, right? That means you enlarge the detachment zone and you decrease the attachment zone, and you do vice versa on the side where you have negative curvature. Here you decrease the detachment zone and you increase the attachment zone. So that means here there will be a surplus of proteins in the cytosol, and here the cytosol concentration relative to the other side of my interface will be depleted. Right? So there will be a gradient from a higher cytosolic concentration to a lower cytosolic concentration. So far, so good. And that's a simple fact of the currents maintaining the interface and the geometry deforming the interface and thereby changing the balance between the currents. And that creates now, because of the gradient of diffusion in the cytosol, it creates a flux. Where does this flux go? Obvious, right? It goes to the right. That means where you had a depletion of particles, they are filled up. And where you had a surplus of particles, you lose them. And that means you're evening out the interface, right? Because you fill the hole that you have on the right. So this interface will straighten. And here we go. That means there is the same effect as you have for mechanical forces. There is a reduction in the length of the interface because of the cyclic fluxes and the geometry. And you can even estimate of what this is, right? Because the gradient delta C that you have here, this will be by geometry the difference in area created by bending it divided by the area, this difference in the area is proportional to two things. It's proportional to how thick this layer of interface is, so it's proportional to the width L of the interface, and it's also proportional to how strongly you bend your interface, so it's proportional to the curvature. But now you should, notice a very close analogy to the relation that we had for equilibrium systems, the Gibbs-Thompson relation. Right, there we had delta rho times the change in chemical potential is given by a surface tension times the curvature. Here the analog is, here you have the curvature, so the surface tension that you create here is proportional to the interface width. Right? So we have an analog of the corresponding Gibbs-Thompson relation, which is, roughly speaking, the relation that you see here. And now we are in business. We have a surface tension. All right. So as said, this is similar to what we had before. This is the Gibbs-Thompson relation, and I just showed you this relation. They are very similar, right? They're basically the same. They just have a different origin. And now let's look at what happens. So once you have that, you can now take this binary model by Stefan Grill and others and make it into a many-component model where you not just have a system of A and P pars, but say you have A, B, and C par, and then you create a system, a multi-component diffusion reaction system, and this multi-component diffusion reaction system at the level of making a model, you can write as some kind of self terms that just concern each individual species and some interaction terms that you have between the species. And I, just for the sake of making a model, I make them to be such that there's feedback, and this you see by the fact that you have here factor exponent 2 instead just of a bimolecular reaction. So it's a model at this point to understand the physics of multi-component diffusion reaction mixtures. You write down this generalized par system as a coupled set of diffusion reaction systems with their respective diffusion coefficients and the corresponding reactions. And because these are proteins which are mass conserving, this is a mass conserving system. So now let's look at what happens when you simulate that. Well, saw it. It shows coarsening dynamics, and the length scale grows over time. And if I would show you the simulation without telling you that behind this is diffusion reaction systems, you could not really tell the difference between the results that you get from a thermodynamic three-component ternary mixture as opposed to the diffusion reaction system. So is the analogy just pictures, or is there more than just pictures? So this is a side note. This is just saying that given this system that you can run on a computer, so I again show the equations and the reactions, you can actually measure whether in this computational model there is a Gibbs-Thompson relation that generalizes to the non-equilibrium system that we have. So the Gibbs-Thompson relation here now is it's in full glory as we derive it in detail in the appendix of this paper. So here is the reference. The object on the left-hand side is our good old friend that we have seen for a while now. It's the mass redistribution potential. And indeed, this again plays the role analogous to the chemical potential, because it's the left-hand side of our non-equilibrium Gibbs-Thompson relation. The delta in the mass redistribution potential is the right-hand side that contains the surface tension, which in our case is the maximum of the two diffusion coefficients and the square root of that, because the diffusion coefficients define a diffusive length scale, which is the width of the boundary, divided by the delta in the densities and the reaction rates in the system. So this is what you'd calculate if you do the theory for the system and do asymptotic expansions, or what you would guess based on my heuristics. And these are the data of this diffusion reaction system showing that indeed this is what you have in the actual data. It's this linear relation between the jump, the change in the mass redistribution potential and the curvature kappa of the interface. Okay? So it's not a hallucination of us that this is true, it's actually really true. Now what does that mean? Well, if this is surface tension, then maybe I should check on this. Maybe I should check on the Neumann law first, and that just means that the surface tension which I defined for my non-equilibrium system, should or should not obey this Neumann law. Why is it not clear that they should obey the Neumann law? But say there are surface tensions. What's the reason for this law? I told you mechanical equilibrium, but also thermodynamic equilibrium. So this law is based on thermodynamic equilibrium, so it's based on the existence of a free energy functional. So it's based on gradient dynamics in the end. Now, this system has no gradient flow. The system has not a free energy. It's a non-equilibrium system, so it's not guaranteed that you have the same kind of law. All right, so this is the Neumann law, and this is what we get. And that's really cutting things short, because I don't have the time to show you all the details of the derivation. So the issue is, or the point is, on the right-hand side, there's not a zero, but there is a force. And we call this F core. And what we can show, what Henry can show in his calculations is that this force on the right-hand side comes from the circular part of the dynamics, right? So from the rotational part of the flows that you have in the system. So not due to any kind of gradients. And then you can use that, so this new generalized Neumann law, to design interaction rules, meaning you design the parameters that appear here in the self-interaction or here in the mutual interaction, such that you tune the phase behavior. And what you can do is the following. Here is the angle alpha A. So this alpha A, as you can see, is the angle here of this blue phase with the neighboring phases B and C. And what Hendrik did here is he changed the mutual suppression rate. There's another circuitry, didn't really explain this well, but he changed the reaction rates in this circuitry, and by changing the reaction rates in the chemical reaction cycle, you can change the interface. You can make it such that this angle here becomes different from 120 degrees. It actually goes down and down and down up to a point where you have this angle vanish. So that means in these non-equilibrium systems, you can have a phenomenon that's also well known from soft matter physics, which is called complete wetting. So you have an interface between the two, wetting the two phases completely. Right? That's one phenomenon. You can do much more with this. You can engineer and design basically all kinds of mixture structures that you like. This one. So coarsening law, that's of course something we also looked at. Over time it does this, you saw this in the movie, and the coarsening law is 1/3. Okay? It's the same as the Ostwald ripening dynamics that you have in your system, so you find the same kind of behavior. Yeah, I don't want to emphasize that. Let me go to the next one. So this is models. This is playing computer games and trying to find out how non-equilibrium physics can give rise to similar things as equilibrium physics. And remember, I mean, all your things you do, you should, at the end, somehow link to the reality, meaning to some experimental measurements. This here was a set of data that was lying around for quite some time. It's data from Petra Schwiller's lab, the PhD thesis by Philipp Glock in 2019. They published that, and they didn't really make much of it. They just published it and said it's a labyrinth-like structure. Okay? Now, after we realized that there is surface tension in these models, we were like, we have to reanalyze these data. We have to see what this really is that you see there. So we asked ourselves the questions, are these foams? Now, foams, in the sense, do they obey the same mesoscopic laws as foams, right? These things are not foams in the sense that they're made out of liquid and interact by pairwise interactions. So are these foams in the sense of, do they obey the same laws, the same mesoscopic laws as liquid or dry foams do? All right, so you analyze the data, and you ask yourself about the meeting points of the edges, so about the vertices. So how can you characterize the vertices that you have in these patterns? And by the way, these blue lines that you saw are the min-E proteins, and the reddish stuff are the min-D proteins. Okay? So the bubbles are filled with min-D, and the boundaries are made by the min-E. So let's look here, not at the above picture, but let's look here at the statistics. So when you analyze all these pictures and do the counting, you find that the angle with a very small standard deviation of 11 degrees is 120. And that's one of the plateau laws, so tick. This seems to be something that matches. Then you can also do the counting about the number of edges that you have in this foam-like structure. And indeed, this is centering around the mean, which is 5.7. That's quite close to 6. Again, check. This is one of the laws that I showed you for a foam, and it's just dictated by the topology. This here is kind of a different thing. So if you look at that, this is the min-D domain size, so the domain size of these reddish areas, and that's actually a constant distribution, and that's not broadening as far as we can tell, right? There's always a question of how long did you look at the experimental data, and is this converged, is this steady state? But as far as we can tell from the data, there is a steady state distribution that doesn't further coarsen, so coarsening is arrested in these systems. And that's different from a foam, because a foam would coarsen to the end. And something that's related to this, and an indication of something that could happen, is, I'm not sure you can see this, it's not so clear from the pictures, but in between these bubbles, there are sometimes blue spots. I can't see them right now, maybe you can. And also, if you look here, there are some interfaces that are quite incomplete, and this seems like there is an interface that actually is emerging, like in a cell division, where this cell here would divide into two. Okay? So there might be additional effects, and not just the coarsening effects that's on which the foam physics is based, but some opposite effect, creating new bubbles or creating new domains, T1, T2 transitions, or similar things. So next thing we did is, because we actually do have quite a quantitative model, computational model for the min system, we said, well, let's also simulate that based on really a quantified model, which I showed you, I think, 2 days ago. So we trust this model to a large degree, and that means now we can check what happens for that model in the parameter regime where you see foams. So you see foams, and they look very similar to the foams that you have in the experiment. And that's not really fine-tuning. This is a very, very broad parameter regime. You also get 120 degrees, and you get the number of edges being on average 6. So that corresponds to the same kind of physics that you see. All right. Now let's go on and see how we can check this guy, the von Neumann law. Is that also true? Right? It seems to be true already by saying there is an average 6, but still there's dynamics associated with it that we want to check. So are the 6 really staying constant in size? Are the 5 shrinking? And are the 7s growing? And for that, you can play the following trick. You have a simulation. This is now a simulation, and the blue stuff is now the min E. And you have this steady state of the simulation. And now you take the steady state of the simulation and you shrink it down. Meaning you make your bubble sizes smaller than they are in equilibrium. That means this system is now quenched to a state out of equilibrium, and it should evolve towards equilibrium by a dynamic process. And let's see what that dynamic process is. So it goes quick, but this was, and I'll show you the data in more detail. You had these typical transitions for foams where the 5s shrink and have a T1 transition where they create a new topology of the system. So for that, it seems it obeys von Neumann's law. But it should be no surprise that this obeys von Neumann's law. What did I tell you? Once you have a surface tension, wherever this comes from, I do not need to specify from this point on where the surface tension comes from and the laws connecting this with curvature comes from. All I need is that I have a flow here in von Neumann's law that's proportional to curvature. That's all I need. In our system here, the diffusion reaction dynamics gives a flow, a velocity of the boundary that's also proportional to curvature. That's something you can check. It's true for this system. And once you know this, once you know that's proportional to curvature, well, you just insert it into the corresponding equation, and you do nothing but using Gauss-Bonnet theorem, and you get the same result. There is no pressure here. Yeah, so what drives the dynamics of the interface? Yeah, so the dynamics of the interface is driven by the very same thing as I had it before. You have a curved interface, which is then trying to move.
And then you have
Yeah, so it's the same thing. It's also trying to make a minimal surface. It's the same tendency, and it's that this curved interface moves. All right. So that's a very robust statement just by the geometry and this fact, of course. That's something you need, right? If you can't show that, this is not true. But if you can show it, it must be true. There's no other way. And that also means if you have another diffusion reaction system which is not based on mass conservation, this is not essential here. All you need is that there is a velocity proportion to curvature. You'll get the same kind of behavior. Of course, given that the pattern that you have is a foam, right? That's, of course, what you put in. Now here, let's look at the numerical data a bit more in depth. So the blue lines are for the 7s, the 6 are in black, and the reds are in red. And you see clearly that this obeys this law. What's different from this law here, right? You might see the coefficient in front of that law doesn't care about Ni. It's the same. Here it's different. So that these slopes here are different for the 5s and the 7s. So it is still the same law, but there is a difference in terms of the prefactors that you have. How am I doing in time? I lost bit track. Ah, yeah, perfect. So we do have the analogous of the von Neumann law for the coarsening of 2D foams for these pattern forming systems. And therefore, yeah, 2D. Oh, wait a minute. So they are quasi 2D. They have a membrane layer and a cytosolic layer, which for simplicity, we took both to be two-dimensional. And then the currents are coming from the exchange between those two parallel compartments.
So there's no 3D currents in the experimental.
Quasi 3D. In the experiment, there is. This is 3D.
Yeah.
In the simulation, just to be able to do this.
Yeah, but in the experiment, it's
3D.
It really is 3D, right?
It's a surface.
Yeah.
It's a typical in vitro experiment
yeah.
with some fluid on top.
But there is a 3D version of the von Neumann law. That was worked out by Svolovich and
Yeah.
others.
So the foam itself is a surface foam.
Oh, I see. Got it. Thank you.
The system is 3D. The foam is 2D. And of course, I mean, there's beautiful work on three-dimensional foams, and it would be nice to have something similar also in the fusion reaction systems, for sure. Yeah. Good point, Nigel. All right. So, and for that reason, okay, because I now checked a few boxes, so I checked the box of the von Neumann law, I checked almost the box of the Neumann law up to this term coming from the curls in the flows. And we do have these plateau laws as well. So therefore, I would suggest to call this a Turing foam. Okay? And maybe, I'm allowed to do that because we have been the first to see that. Now, what about the other way around? So this was forward topological transitions, T1s, that you saw here. What about the other way around? And for that, you need to do the opposite. You start from something too big, and you want to know how is it going back to the smaller size. Okay? And this shows here what happens. So if it's too big to begin with, then look at these two squares, I and double I, where two different things happen. Here, what happens is you get a little spot. And this little spot is growing into a boundary. So it creates a cell division by nucleation, right? It's a nucleation event that you have here. And this is the same event that you see when you look at the simplified reduced model, which we called the two-component mass-conserving diffusion reaction model, that breaks the mass conservation. There you also see domain splitting. And this is a similar effect that you see here. Okay? The other effect that you see is not a nucleation event in the middle, where the domain becomes too large and you find a new pattern in the middle. The other effect is that as this thing grows, the domain boundaries of this bubble deform, and then it seems that this deforming domain boundaries do have another instability, which is an interface type of instability, where this interface here is unstable and forms a new interface between the two bubbles that you see here. Okay? That's still something we're trying to explore and understand better of why this happens and how this happens. So you do have, and that's what we call kind of backward topological transitions. You can also call them cell division, whatever you like. But they are the counteracting forces to von Neumann's law. So von Neumann's law drives the coarsening, and there's a counteracting effect from domain splitting and nucleation events that drives the opposites, and therefore these foams don't coarsen. They remain in a steady state with a non-equilibrium distribution, steady state distribution of bubble sizes and bubble edge numbers, etc. You can play games and put this on spheres. For us theoreticians, it's sometimes a game to put things on spheres because then you see interesting effects of topology, and you do, because there's reason for things to be different on a sphere, since there's the Hairy-Ball theorem from topology, and then that's kind of also underneath that. But why would you do this in experiments? Cells are spherical? Yeah. Very obvious reason. But why would you do it in an experimental system? What would you gain, maybe? Any ideas? Think of, the fact that I said you can try to use these models to understand biological phenomena, but you can also hijack the understanding of the biological phenomena to contribute to synthetic cell research. And in synthetic cell research, a major question is, how do you actually define midplane, such that some subsequent mechanism could localize midplane and therefore try to do cell division at midplane. And here you go, right? Here you have, now let me call this quote, quote, cytokinetic ring. It's not a ring at all, which is cytokinetic, but it at least has, a template that you have there, and maybe in subsequent work people are able to link the mean protein systems with other protein systems to make this into a contracting ring. So what are the interface laws of Turing foams and mixtures? This is my summary. So one point of the story is cyclic attachment, detachment currents induce non-equilibrium surface tension. And as said, I think this is rather general because it's just based on the fact that you have non-equilibrium currents localized at the interface. Of course, you could have the opposite effect, right? So my story depended on the attachment and detachment zone such that the gradients even out the surface length. It could be such that this enhances the difference that you have. And then you would have something that gives rise to a instability with a negative surface tension, something I guess you cannot have in equilibrium, but something you could have in such a non-equilibrium system. You have a reaction-driven Gibbs-Thompson relation that generalizes the Neumann law because there's curls in the reactive flows, and you can use that to design patterns or design multi-component mixtures of reacting components. And the third point, this was my last point, is that there are generalized laws for coarsening that give rise to a steady state. So here's the future. This is the same foam, and on this same foam is not a cell. This object that you see there is a vesicle. There's nothing but lipids in this vesicle, so it's just a lipid bilayer. There's no motors, there's no cytoskeleton. It's only this foam-like min structure on the bottom at the surface at a supported lipid bilayer and this vesicle on top. And this vesicle on top, so there's a cartoon here so you can envision what this is. This is the foam-like min system. This is the vesicle. There are min proteins all over the place. And this gives rise to cell-like motion. How this happens in detail is not so crystal clear, actually, because you need to now study and understand how proteins change the geometry of vesicles, how the changed geometry back effects on the pattern-forming system, and how the mechanistic details work out to give the cell-like motion. The ideal person to talk to is Jan here in the audience. It's your poster, right? So let me conclude with that, and thank you for your attention.
Questions?
Lovely talk, as usual. I want to ask you about just the last slide. So the vesicle is moving, but it's also changing the pattern.
Yeah,
So it's changing the surface tension of the pattern.
Yeah, yeah. And that's a very important and key observation, that there's feedback between geometry and pattern formation.
Yeah.
And that feedback is
bidirectional.
essential for this thing to move.
Yeah.
So the future goal of quite a large research area in my group is, how is pattern formation linked to a changing geometry? And how do they feedback with each other?
Right, but it's not changing the vesicle as it moves.
It changes.
Is
so if you
it
look closely,
changing?
the vesicle is wobbling,
Yeah.
and it's not symmetric on the two sides.
Right.
And at the moment, so if this is the surface on which you have the pattern, and here you have your vesicle, so that's my vesicle, that's the surface. Then there's patterns here, and there's also mean proteins here on the outside of your vesicle. And there's now various ways of how this pattern could interact with that pattern on the surface. Either the mean proteins here, by attaching to the vesicle surface, induce spontaneous curvature and bend this object, or the vicinity of proteins in the wedge that you have between the surface and the vesicle is such that the proteins actually have some forces, real forces, dimer formation, some lock and key type of dynamics that could then be like a zippering mechanism, such that the vesicle is zipped along the patterns that you have on the bottom.
But do the proteins from the pattern go into the vesicle?
Yeah. No, not in. So inside is no.
No, I mean onto the surface of the vesicle.
Yeah, there's patterns here.
So that's why the surface tension is being modulated by the presence of the vesicle.
Yeah, and there's patterns here. And because there's this small wedge, there's the height of the pattern changes. And since those patterns here can change, can sense the geometry as this vesicle moves, it changed the amount of cytosolic reservoir, and that changes the patterns on the surface.
So can you do an experiment where you have two superimposed patterns, like a layer? One layer has got one pattern, one layer has the other. They're in contact at an interface, and then will they do some dance?
Yeah, I would love to see that, and I'm begging Petra to do these kind of experiments, to have different patterns on different vesicles, on different surfaces. The different patterns could be, could be one pattern here, one pattern there. They could change the geometry. That could influence the pattern. They could have some effective interaction. They could communicate. So there's a whole story you can build around this. Yeah.
Can you vary the size of the vesicle?
In some limits.
Okay.
In some limits. Yeah. And remember, for them, this means quite some effort. And I hope they make the effort.
So I imagine that the persistence length of the cell-like motion would be dependent on the ratio between the size of the vesicle and the fold size.
Yeah, the persistence length is something they didn't really look into. So at the moment, this looks like a straight motion, kind of wiggly. So what I would expect, it's a persistent random walk type of motion, but maybe more coherent than that. And of course, it depends on the mesh size that you have and on other things. Yeah. Yeah.
Any more questions?
Well, I'm really amazed. It's beautiful. I was wondering whether vertex width provides some information about the underlying dynamics of the system.
Say it again, whether
the vertex width, how width it is.
You mean the width of the edge?
Right.
Yeah, the width of the edge is the surface tension, basically. The broader it is, the higher the surface tension, and what the width is dictated by is the diffusion coefficients of the proteins on the membrane, basically. of the various components that you have, because just by scaling arguments, you can say a diffusion constant is micrometer squared per second. You multiply by a time, you get micrometer squared. You take the square root, you get a length. So it's telling you, or you can tune it, let's put it this way, you can tune the width, therefore the interface tension, by changing the diffusion, the diffusion coefficient. Done?
If there are no more questions, I think we should give Erwin a big round of applause for this really beautiful series of lectures.
Thank you.
Before we go for lunch, I just remember that today is a holiday, so some places are closed. I send you an email with a place that I know for sure it's open. It's a little bit farther than usual. And on the way there, you may find others that are open, but that is for sure. That one is for sure. It's just the way, I mean, here I don't know if you have been going to these kilos for lunch, but basically it's this main street here on the left, continue straight, and then we'll